Today we'll be covering section 12.4 on the addition and complement rules. Before we begin, I want to say that most of the problems in this section can be solved using techniques we already know. But occasionally we'll come across certain problems when we need to learn a little bit more about probability, and occasionally we'll find out that it's convenient to use some more formulas and have them in our toolbox. So I'm going to do something that I don't usually do. I'm going to go ahead and give you a listing of the formulas that we're going to add to our toolbox in advance of when we've actually talked about them. I think it'd be good to let you look at what we're going to be using, mainly for the reason that I said earlier, we don't always even need them, but they will be here when we do need them. The first is called the addition or union rule for probabilities. It simply says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And remember, or means union and means intersection. The complement rule. If E is an event and E with a superscript C is the complement of the event, then the probability of E complement is equal to 1 minus the probability of E. The product rule for independent and dependent events. If two events E and F are independent, then the probability of E and F is simply the probability of E times the probability of F. Now the dependent version of this rule uses some notation we haven't even introduced yet, but I'm going to go ahead and do it anyway. We'll come back to it later and talk more about what the new notation means. But it says, if two events E and F are dependent, then the probability of E and F is equal to the probability of E times the probability of F given E, which is also equal to the probability of F times the probability of E given F. Remember, I haven't even introduced that notation where the vertical line is used here in this context yet, but I will. That leads to something called conditional probability, and I've got two formulas related to that. One says the probability of E given F is equal to the probability of E and F divided by the probability of F. Remember, when I say E and F, and means intersection. Also, the probability of F given E is the probability of E and F divided by the probability of E. Before I leave this, I told you I'm going to rotate back to this later, but I will say, if you use that notation with the vertical line, it's read the probability of E given F. The vertical line is read as given, or given that. So of course the probability of F given E when the E and the F are flipped around the vertical line. Like I said, we'll come back to this later, but this is the addition to our toolbox of formulas. Sometimes we'll need them, sometimes we'll just be able to go back and do these problems using the things we already had, but they're there if you need them. Suppose we want to calculate the probability of rolling two dice and getting a sum of either 5 or 9. And you notice I call this getting a sum of 5 an event called E sub 1, and the sum of getting a 9 an event called E sub 2. That's just for convenience. We're trying to roll two dice and find the probability of getting a sum of either 5 or 9. You really don't need any of the new formulas to do this. This is just like a problem we might have been able to work earlier, and I want to emphasize that what you really need to do is build your 2x2 table for rolling two dice, which gives you the sample space, and then look, we're looking for a sum of 5. That's the event I called E sub 1. There are 4 possibilities. You roll 4, 1, 3, 2, 2, 3, or 1, 4, or a sum of 9. That's the event I called E sub 2. There happen to be exactly 4 possibilities for that as well, either a 6, 3, a 5, 4, a 4, 5, or a 3, 6. So the probability the sum is either 5 or 9 is simply how many ways you can get a 5 or a 9, which happens to be 8, over the number of ways you could get any sum, which as we know from earlier problems is 36. WebAssign will accept 836 as the answer, or you can reduce it to 2 9s. But there is something about those last two examples worth noting. There's a difference. Look at those two. I'm flashing on the left, the first one I did, on the right, the second one I did. Going back to the one on the left, the probability the sum was 5 or 7 turned out just to be the sum of the probability that the sum was 5 and the probability that the sum was 7. In other words, there were 4 events that gave me a sum of 5. So the probability of getting a sum of 5 is 436, but there are also 4 that gave me a sum of 8. So the probability of getting a sum of 8 is also 436, and 436 plus 436 is 836. But if you look on the right side, the probability that a number is greater than 2 or odd turned out to not be equal to the probability that the sum was 2 plus the probability that the sum was odd. If you look at it, the probability that the sum was 2, 3, 4, 5, 6, 7, 8, 9, 10 was 8 out of 10. The probability that the sum was odd was 5 out of 10. Well, obviously, 8 tenths plus 5 tenths is 13 tenths, not 9 tenths. So on the left, I was just able to take the two events separately and add up the probabilities and get the correct answer. On the right, if I tried that trick, it wouldn't work. Why is that? It's an important distinction. Think about it just a minute. In a nutshell, it's because on the right, some of the values are greater than 2 and odd. Remember that when we did this problem on the right, there were certain numbers that were both greater than 2 and odd. For example, 3 is greater than 2 and odd, 5 is greater than 2 and odd, 7 is greater than 2 and odd, and 9 is greater than 2 and odd. So there's an overlap between those counts. On the left, that didn't happen. When you looked at the numbers that summed to 5 and the numbers that summed to 7, there was no overlap. That's what caused the difference. Noting this leads to an important result called the addition or union rule for probabilities. Remember, that's one of the ones that I flashed up earlier. It says that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. And if you look at that formula, it encapsulates the difference that we just noticed between those two earlier examples. You could have used this rule to solve both of the earlier problems, but you don't have to. We were able to figure out a way to do it without using the formula. But I will say that if you did use the formula for the first one, where the events were mutually exclusive, the sum being 5, there was no overlap with the sum being 7, there was nothing to subtract away. If you take that minus part of the formula, it would have been 0. The probability would be 0 that a sum could be 5 and 7. However, on the second one, there was an overlap. There were numbers bigger than 2 that were also odd. This formula takes care of that. Think about that, what that means. If the events are mutually exclusive, the probability of them both occurring together is 0, so you're actually subtracting nothing. So the formula also allows for the possibility that that overlap is not probability 0. So the formula works either way, but if they're mutually exclusive, remember there's just nothing to subtract. The formula just degenerates to having to subtract nothing. Now let's look at some problems where we might want to think about it in terms of using this formula. If we select a single card from a standard 52 card deck, what is the probability that we draw either a heart or a face card? So the probability of a heart or a face card. Recall what this standard 52 card deck looks like. It has 4 suits, 12 face cards, etc., etc. So the probability of a heart or a face card is just going to be the number of hearts or face cards over the number of cards in the deck. Well, if you look at the hearts or face cards and just count them, the face cards are the cards that actually have faces on them, and you've got the hearts as the other possibility. If you just count, you'll see that there are 22 of them over the number of cards in the deck, which is 52, so you get 22 over 52, and if you want to reduce it, you get 11 over 26. Suppose I wanted to actually use that addition rule rather than just figure it out as I just did here. It would still work. I would just simply take the probability of getting a heart. Well, remember, there are 13 hearts in the deck, so the probability of getting a heart is 13 over 52. Then I would calculate the probability of getting a face card. Well, there are 12 face cards in the deck, 4 jacks, 4 queens, 4 kings. So the probability of getting a face card is 12 over 52. And if I apply the formula, I'll see that I still need to calculate the probability that a card is both a heart and a face card. And if you look at the picture, there are 3 hearts that are also face cards. That's the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So the probability that the card is both is 3/52. And if you plug into the addition rule formula, you'll notice that you get the probability of getting a heart is 13/52, plus the probability of getting a face card is 12/52, minus the probability that you get a card that's a face card and a heart. That's 3/52, and that's 13 plus 12 minus 3 is 22. So you get 22 over 52, which is 11/26, which is exactly the answer we got earlier by doing it without using the addition rule. So this is just another example of where the addition rule works, but you could really do it without it. Here's an example where using the rule is really the best way to do it, the most straightforward way to do it. It says if the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B is 0.2, find the probability of A or B. Remember, and is intersection, or is union. So I would say the most straightforward way to do this particular problem is to use the formula. If you write the formula down, replacing E and F with A and B, you get the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Well, we know the probability of A is 0.3, we know the probability of B is 0.4, and we also know that the probability of A and B is 0.2. So a little bit of arithmetic tells you that the final answer, the probability of A or B, is 0.5. That's the most straightforward way to do it. Another example where the formula is the most straightforward way to do it. What if the probability of A is 0.3, the probability of B is 0.4, the probability of A or B is 0.5, but this time we're looking for the probability of A and B. So it's the same formula, but you know different things. Here you know the probability of A or B is 0.5, the probability of A is 0.3, the probability of B is 0.4, and you're looking for the probability of A and B. It becomes a small algebra problem, but it's easy enough. 0.3 plus 0.4 is 0.7. If you move the negative probability to the left and move the 0.5 to the other side, making it negative, you'll end up finding that the probability of A and B is 0.7 minus 0.5, which is 0.2. These are both examples where using the addition or union rule for probabilities is the most straightforward way to solve the problem. Use the following table to find the probability that a randomly chosen member of the Student Government Board is a freshman or lives in off-campus housing. They give you a table. This is another problem where you probably can just do it by the old techniques. You want to know the probability that a person is a freshman or lives off campus. So you look at your chart. There are 5 freshmen and there are 5 students who live off campus. So we want to know the probability of being a freshman or living off campus. You can't just say 5 plus 5 because there's one person who overlaps. There's one person who is a freshman but also lives off campus. So when you count the number of freshmen or students living off campus, you have to say 4 plus 1 plus 4. That's only 9. And then when you count everybody, you get 4 plus 1 plus 2 plus 0 plus 4 plus 2 plus 1 plus 0 plus 4 plus 0, 0, you get 17. So the answer is 9/17. Again, you could use the addition rule to get the answer, but I would recommend just doing it straightforwardly. Consider the experiment of rolling 2 dice. Let A be the event of rolling a sum of 8, and let B be the event of rolling a double. A double means you get the same number on both dice, like a 2 and a 2 or 5 and a 5. Find the probability of getting either a sum of 8 or a double. Again, when you're rolling 2 dice, you think of that as a 2-stage experiment, so you build a table. We've talked about that before. The probability of getting an 8 sum or a double is going to be the number of ways of getting a sum of 8 or a double divided by the number of ways to get any sum. So if you look at the numerator, let's first look at the number of ways of getting a sum of 8. You could get a 6-2, a 5-3, a 4-4, a 3-5, or a 2-6. Then look at the number of ways to get a double. You could get a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. If you want to count all those possibilities, notice there's an overlap of 4-4. So when you're counting, you don't want to count that 4-4 twice. If you count them, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't count that 4-4 twice. So that gives you 10 over the number of ways to get any sum. Well, it's, as we've learned from doing these type problems multiple times, there are 36 possibilities. So the answer is 10 over 36, and if you want to reduce it, you get 5/18. Again, we didn't have to explicitly use the addition rule for probabilities, although you could. Let's go to the complement rule that we introduced in our toolbox at the beginning. The complement of an event. Let's take an experiment where we're rolling a single ordinary dice. The sample space obviously is going to be either 1, 2, 3, 4, 5, or 6. So if we want to look for the event that we rolled a 3, the probability of doing that is the number of ways you can get a 3, which if you're rolling a single die, there's only one way to do that, over the number of elements in the sample space. So the probability of rolling a 3 is 1/6. The complement of that event, and we're going to use the notation E with the superscript C. Some texts use E with an accent symbol like we used back when we talked about regular set operations, but if you see it either way, it means the same thing. E with a superscript of C or E with an accent symbol. It's sort of, in a sense, the opposite of the event. So if you're looking for an outcome, the complement is everything except that outcome. So if we're talking about the problem we did above, if the event E was getting a 3, then E complement is not getting a 3. So in this case, if we wanted to write out E complement, it would be everything except 3. So it would be 1, 2, 4, 5, or 6. So when we're talking about the complement of event, that's what we mean. Everything but what makes up the event. There are 5 things that aren't 3s out of possible 6, so you get 5, 6. And notice that the probability of getting a 3 is 1/6, and the probability of not getting a 3 is 5/6. And that's not a coincidence. That's what the complement rule says. It simply says if you know the probability of an event and you want to know the probability of the complement of the event, you just say 1 minus the probability of E. And the importance of that rule is, it seems sort of obvious, but it's very useful because some problems it's really easy to calculate the probability of an event, and it's a little more difficult, or more than a little more difficult sometimes, to calculate directly the probability of the complement. But if you can calculate the probability of the event, all you have to do is say 1 minus that probability, and you'll automatically have the probability of the complement of the event. So this is important. It's a very handy tool to have in your toolbox. For example, if I ask you to find the probability of not rolling a sum of 11 when you're rolling 2 dice, again, you'd build your table. The probability of not rolling an 11 is the same thing as 1 minus the probability of rolling an 11. The probability of the complement of something is 1 minus the probability of that something. So it's very easy to calculate the probability the sum is 11 because there are only 2 possibilities. You can get 6, 5 or 5, 6. So the probability of getting a sum of 11 is simply 2 out of 36. So the probability of not getting a sum of 11 is 1 minus 2 out of 36, which would be 34 out of 36. Complement rule is a very powerful tool in your toolbox. If you want to reduce that to 17/18, you're free to. I want to talk about a little bit about the English language as relates to this. It turns out that when we're doing probabilities, we tend to come to these problems where we're asked to find the probability of at least one something. And I want to talk a little bit about that in particular so that when you see it, it won't be confusing. For example, if I roll a standard die 3 times, What's the probability we get at least 1 4? You see that at least 1 quite often. At least 1 4. Well, think about it. At least 1 4 means you get exactly 1 4, or exactly 2 4s, or exactly 3 4s. That's what it means to have rolled at least 1 4 in the context of rolling the die 3 times. One way to answer this question is just to do 3 separate probability calculations and just add up the results. Just find out the probability of getting exactly 1 4, then find the probability of getting exactly 2 4s, then find the probability of getting exactly 3 4s, and just add them all up. That's one way to do it. You could take this, and this, and this, and just add up the 3 separate probabilities. That's quite a bit of work. There's a better way. The better way is to use the complement rule. Because if we roll the die 3 times, there are only 4 possibilities altogether. We've talked about 3 of them. We've talked about getting 1 4, or 2 4s, or 3 4s. There's only one other way, and that's to get no 4s at all. So wouldn't it be much easier to calculate the probability of not getting any 4s and then say 1 minus that? And that's what I'm going to do. The complement rule says the probability of getting at least 1 4 is 1 minus the probability of getting no 4s, because getting no 4s is the complementary event of getting at least 1 4. And getting no 4s is a much easier probability calculation. So how do we calculate the probability of getting no 4s? And this comes back to the stuff we talked about earlier. Remember when we started studying this, I asked you if you know how to count. The solution of that problem requires us to count using some of our combinatoric formulas, and that's why we studied them, so we could use them. So if a standard die is rolled 3 times, what is the probability we get at least 1 4? Well, we just talked about that the easiest way to do it is to calculate the probability of getting at least 1 4 as 1 minus the probability we don't get any 4s. That probability of getting no 4s is the key calculation in the whole problem once you understand what you're trying to do. So how do you calculate the probability you don't get any 4s? Well, I would think of it this way. The probability of getting no 4s is the number of ways to get anything but a 4 divided by the number of ways to get anything with your 3 rows. I think I'll start with the denominator first. Let's find the number of ways to get any 3 rows. Going all the way back to the counting principle, if you're looking for the number of ways to get any 3 rows, remember each row can be a 1, 2, 3, 4, 5, or 6. So think of this as a 3-stage experiment. You can look at how many ways you can get something for row 1, row 2, row 3. The counting principle says to multiply them together. So the number of possibilities for the first row, well, there are 6 possibilities. As for the second, there are still 6 possibilities, and for the third, there are still 6 possibilities. So the counting principle says the possible die rolls you can get when you roll 3 times is simply 6 times 6 times 6, which happens to be 216. That's the denominator. But what about the number of ways to get anything but a 4? Well, after having done the calculation we just did, I think you'll see that it's pretty easy to look at the numerator and see that it's the same thought process, but this time we're not allowing the possibility of getting a 4 because we're looking for the number of ways to get anything but a 4. So we knock the 4 out as being a possibility, but the process stays the same. We're still doing 3 die rolls. We just don't want any 4s. So there's only 5 possibilities for the first die roll if you don't want it to be a 4. There are only 5 possibilities for the die roll 2 if you don't want it to be a 4, and there are only 5 possibilities for die roll 3 if you don't want it to be a 4. 5 times 5 times 5 is 125, so the probability of getting no 4s is simply 125 over 216. But that wasn't the final answer. We want to know the probability to get at least 1 4. The key calculation was getting the probability of no 4s, but it wasn't the final answer. The probability is 1 minus that, which would be 91 over 216. How about this? If you draw 3 cards from a standard deck without replacement, what is the probability that at least one is a face card? Write your answer as a percent rounded to 1 decimal place. So as we learned, the probability of at least one something is 1 minus the probability of none of that thing. So in particular, the probability of at least one face card is 1 minus the probability of no face cards, or 0 face cards. And as we've seen before, that probability of 0 face cards is the key calculation. Well, what is the probability of no face cards? There are 12 face cards in the deck. We've done this multiple times, so that means there are 40 cards that aren't face cards because 52 minus 12 is 40. So we think of partitioning the deck into face cards and non-face cards. There are 12 face cards, there are 40 non-face cards. So the probability you don't get a face card is the number of ways not to get a face card. In other words, the number of ways to get anything but a face card divided by the number of ways to get any 3 cards. We've done these problems in earlier sections. When we're drawing face cards, we don't care about order, because when you pull a card out of the deck and put it in your hand, it doesn't matter what order the card came into your hand. So this is a combination. If we're trying not to get a face card, we've got to draw from the 40 things that aren't face cards. So it's a combination of 40 things, and we're choosing 3 cards, so it's a combination of 40 things taken 3 at a time. Down bottom, when we don't care what the cards are, it can be any of the 52, but we're still drawing 3 cards. So it's a combination of 40 things taken 3 at a time, that's the number of ways to get anything but a face card, over a combination of 52 things taken 3 at a time. That's when you don't care what the cards are. You're drawing 3, but you don't care what they are. And in case you really have forgotten your shift combinations to get your calculator answer, I put them there for you. I hope you didn't need it. They ask you to do a decimal approximation, so you need to change that now to a decimal. That's 0.44706. They ask you to change it to a percent rounded to 1 decimal place. So take plenty of decimals because you have to change it to a percent and then round it. So do not just write 0.44, write several decimal places. So it's 0.44706 to several decimal places. So you continue your calculation. The probability of getting at least 1 face card is 1 minus the probability of no face cards, which we've calculated to be 0.44706. Notice I'm emphasizing yet again, carry plenty of decimal places during this calculation. Round off in the very last step. To do that subtraction, you get 0.55294. You're still not ready to round because it says to give your answer as a percent rounded to 1 decimal place. So you first change it to percent and then you round. You sort of see now why I'm emphasizing how important it is to carry plenty of decimal places. Now change it to percent, which means you move the decimal place 2 places to the right, and finally you round that to 1 decimal place.